Okay, this is really meta with the whole
Inception.
yeah. Yes, we will close this blind. However, it's done. Although it actually. There you go. Oh, we've already started, I believe. I thought we have. We should be screen sharing. Let's just double check. Oh, start? Oh, wait, this is now. We don't want to do that. Because it says start broadcast right now.
Yeah, no, definitely it should be working.
Oh, wait, allow.
No, I think it's broadcasting now. It's live.
So I thought we could start off with some really trippy things from my desktop. We're good now, but Bill? Excellent, excellent. Okay, cool. So just let me know if things disappear off the bottom. I think I'm actually going to swap these windows just to make it a little bit easier to see. Let's let these load. In layout, we'll switch source and console. Excellent. My computer's having a little bit of a freak out. Okay, we're just going to restart our studio here. It's sort of lagging on us. All right. Let's see if we can swap these again. Source and console, okay. Now we are going to open recent projects, biomaRt tutorial. Okay, are we all ready? Excellent, excellent. And do you mind if someone should probably check the Etherpad while we do this, just in case someone asks something. But yeah, today we were sort of talking about different topics to teach, and one of the things we wanted to do was go through some bioconductor packages at one point. And this is the one that I suggested, and originally it was supposed to be part of a tutorial, but we just decided to make it a full tutorial of its own because I think it's really great. But what biomaRt actually is, it's basically, it connects to the internet and grabs information from online bioinformatics databases. Like, what databases are we talking about here? Let's just see if I can get, okay. An example here might just be, basically you can get all the stuff from, say, Flybase. You want to talk about a gene, let's say like actin 5C. Hope the internet works. Okay, so it comes with all this information, which occasionally we'll want to use in R as for our analysis. Like, say you want to convert between gene IDs, or you need to grab gene IDs, you can do that. You can also grab stuff like what Go terms it's got, and like where the gene starts and stops in the genome, where it's located, the sequence of its, I don't know, you can get the peptide sequence for every different transcript. You can get the coding sequence of the gene. It's really powerful, and we're going to try to sort of go through that today and basically just sort of go through a couple of examples, one of which was actually a real example that I did recently. So hopefully we should all walk out of here being able to use it. And if you need help with something, hopefully this package can actually solve some of those issues for you. So I guess we're going to open up this biomaRt demo.r file here, and just let me know if things are a little bit too small to see at any point. And then I guess sort of I've already explained what biomaRt is. We're going to load the library. I'm sort of waiting for that little stop sign to go away. And I guess, oh yeah, one other thing, you need to have an internet connection for this to work, because the main part of this package is that it connects to the internet and gets information. So I guess the first most basic function of this package is to just sort of see what data sets and what sort of databases you've got available. And there's this function called, and I'm just going to go through the script, and feel free to follow along through the script. Is sort of, I'm just doing Control-Enter to run a line and skip to the next one. But in this case, I'm just going to run this first one, and it says list marts. I'm going to save that as marts. And then we're just going to sort of look at it here. And you'll see that it's come up with a couple databases. This is just sort of short lists here. We can just click on this to look through all of them. There's a lot. There's a lot of different ones. Basically, there's some which is like Ensemble, which actually have multiple databases here. Then there's others, like such as like, I think there's like Tear, the Arabidopsis one in here somewhere. There's one for C. elegans. There's basically one for almost every animal you might want to work with. And then basically, if you find something you like, so there's the actual name of it with the version right here. And then there's the actual just biomaRt field or something. So when you find one you like, you're just going to sort of save whatever this is. In this case, I'm clicking on FungiMart, but we're actually going to use Ensemble here at the top. And then we're going to basically use this function called useMart. And then we're going to say Ensemble. And what this does is it connects us to that database, and now we're allowed to sort of look around and see what's inside it. There's actually another level of organization beneath just, I guess, sort of the whole which database you're going to use. There's different data sets, and you can see which data sets there are by this list datasets function. And then you just, to list a data set from I'm going to call it a mart, we basically have created Ensemble here, which is a mart, which is something, a database to connect to. And then we're going to say list data sets on that mart. And then when we say look at the data sets, it should come up with a couple different basically data sets for different organisms. Ensemble is sort of organized by species. And there's a couple species here. We're actually going to go, you can also sort of scroll through it by just clicking on the sort of data tab over here. And you can see that there's basically one for almost every organism that I can think of off the top of my head. And so I'm actually going to use, just because the one I'm the most familiar with is the Drosophila one. I work on Drosophila. When we want to use a database or a data set, we basically use that useMart command again. But now basically the first argument is going to be which biomaRt or database we're connecting to. And then the second argument is going to be which data set we want to use. And so now Ensemble basically knows that we want to use the Ensemble biomaRt database with the Drosophila and melanogaster data set. And so now it's actually, we're getting to the point where we can actually start to see what information is there. There's this, when you retrieve stuff, like information from these databases, that's every sort of piece of information, such as like a gene name or like a Go term or like the interpro ID of a protein or something, is going to be, all those are called attributes, I guess, in context of biomaRt. I'm just going to save them here. There's a ton of them, as you can see. If you look at sort of the number we returned here, there's over 1,000 different things. Some of them are copies of each other. There's a little bit of redundancy in there, but you can kind of see this sort of stuff there is. There's like gene ID, transcript ID, peptide ID, all this kind of stuff. If you really want to be hardcore, you can sort of scroll through here. You can also sort of search through it using, there's a function called grep or grep, however you want to pronounce it. That's pretty good for searching for a specific thing. But you can see basically there's almost like every single thing you could possibly ever want. Like you can even get like microarray probe sets for whatever you're searching for. So it's basically, it has all the information you would ever hopefully need in these databases. So why don't we sort of try actually getting information for a test set of genes. And I sort of made this gene list. It was originally 20 genes, but then I thought we were retrieving a little bit too much stuff because it took a little too long to retrieve everything, so I cut it down to 10. We're just going to load it from a CSV, and then I'm just going to sort of take out all the names. As you can see, if we look at sort of this gene list vector, it's just got a list of 10 different names. I've only actually ever heard of one before. There's this one called fruitless, which is involved in sexual differentiation. But the rest of these are just a sort of giant black box, and I have no idea what they do, and I want to find out more about them. And that's where using this package is really great, because sometimes, like, say you'll do like a common application of using this package is, say you've done a microarray or a sequencing experiment, and you've got a whole bunch of genes that are differentially expressed, but you don't know what they do. You could either go online and look at their annotations one by one on the web page, but that would be really slow and maybe take notes. Or you can retrieve the information all in one go with biomaRt, which is what we're going to do here, except for 10 genes. So this function right here, this getBM function, is sort of, I guess, the workhorse that actually does work. So all those other functions that we just covered are sort of like exploring what you can actually download. getBM actually gets the data. So we're going to save what we get as MART data. And then the first sort of argument here is attributes. And then attributes, we've already sort of looked at a few of attributes. Remember, these are what the attributes look like. And we always want the name of what we want is what we use here in the name column. Basically, I'm just sort of basically supplying a vector of attributes I want. So I'm just going to get the ensemble gene ID, which is basically, it's a sort of long, complicated number. It's usually not human readable, and you've got to usually search it to figure out what gene it corresponds to. I'm also going to get the normal gene name, which is what we've got here, the kind that humans actually look at. I'm also just going to get the Go ID for, say, all these have Go terms associated with them. I'm going to get both the identifier, there's a numerical identifier, and then I'm actually going to get the Go term name. I'm also just going to get, just for fun, I just sort of want to sort of show that you can get lots of data from this. I'm going to get randomly the number of transcripts each gene's got, and also whether or not it's got a transmit brain domain. I was just like, and what type it is. So I was just sort of like, that seems fun. So, so these are the things that we want to retrieve, which are called attributes, as we've already said. The next thing, I guess, the concept we need to know is filters. Filters are basically what values are we searching this database by. So basically, attributes are what we want to look for. Filters are what we want to search by. And so a little bit thing before, I guess, of how I sort of made this tutorial. I mean, obviously, if you don't know what these values are, you've got to try a few different ones. However, if you want to see what you can search by, you can use there's this list filters function, which is kind of handy. It's just, basically the function is the same way as all those list data sets, list attributes. It'll just give you a list of different filters you can use. And then the values are what we actually want to search by. They're going to be whatever type of thing you specified here. And so in this case, flybase name gene corresponds to these sort of normal gene names. These are the actual values I'm feeding it. And then obviously we have to say which MART we are going to get the values from, which is basically at this point, it's the biomaRt database and as well as the data set. So I'm just going to run all of this. I'm going to just control enter through this. It's going to take a second or two, probably. Oh, it actually seems to have retrieved it almost instantly, which is a rare thing. But if we just look at it, so we can sort of look at it with the structure function. We got all these ensemble gene IDs. Again, not human readable, but they're still pretty useful sometimes. Here's the actual gene names. You'll notice we got multiple copies of each gene name. The Go IDs, the numerical IDs, what these actually IDs stand for, and then number of transcripts for each of these genes, and whether or not it's got a transmembrane domain. You can sort of look at it just by clicking on it here. You'll also notice that we have a lot of different entries, multiple entries for every single gene, which is, you're like, hey, why is that? Basically, if it's ever possible to retrieve multiple values for something, it'll basically create duplicate entries for each one of those multiple values. And you'll notice that, so these Go terms only pop up once, and so each line is a new Go term, I guess. However, stuff that is the same between all of them, such as the number of transcripts, that's obviously not going to change with the number of Go terms, is always the same for that. So you just sort of have to be a little bit it's sort of something you've got to be expecting when you get data back from this. Also, it's sort of whatever you search by, it sort of has a tendency of alphabetizing things in a certain way, or like the order is sort of totally random, so you can't count on the order of what you get back. But regardless, for this very first query we made, we already got a ton of data that would have been a few hours, or actually maybe not a few hours, maybe like an hour of clicking around online and writing it down in our lab notebook or something. And also notice that we got, so basically I'm just looking for the, so this is sort of the list of genes from that data we just retrieved. I'm going to get all the unique entries and then the number of those entries that appear. We got data for all 10 genes. So there was 10 genes in that gene list. And so one other thing that we can sort of want to do, so what if we want to search, I guess, sort of another way? We started off having like an entire gene list, like we had 10 genes that we wanted to know more about. What if we wanted to find all the genes in the genome that do a certain function? Such as like, in this case, we're searching by GOAT term, but you could search backwards by another filter, I guess, as well. So in this case, I was sort of scrolling through here. Oh, someone's trying to get in. Oh, excellent. Hey, Andrew. But basically, we noticed that one of the genes, G alpha Q, I was just like, oh, look, it's well, one of these ones along here was basically, it was saying it was a GTPase. So I forget where that was. Oh, yeah, here it was, this term. So I took the Go ID here, and I was like, why don't we search the entire biomaRt data set for Drosophila for this particular ID? And basically what we do is we're just looking for all the gene names, that sort of those ensemble gene IDs, which are, again, not human readable, and then all of the actual gene names. And we're sort of we're searching by Go ID, which is the Go term ID, and then this is the value we're going to search by. You can also put a vector of values here if you wanted to search by multiple things. And again, we're using that ensemble thing we specified earlier. Huh. You know, that might work, and I've never tried it. So I guess the only way to know is to try it and see what comes out. So that would be potentially very awesome. But when we run this query, again, we got 147 different things back. And these are, I guess, everything that's got, I guess, this Go ID in the Drosophila genome. So we got literally every GTPase, as long as they've been annotated as such, which is pretty powerful. Now, what if we wanted to get, I guess, say, nucleotide sequences, such as like, say, because currently all we've been searching for is, I guess, just sort of information about a gene. What if we wanted like the gene itself? Or in this case, we're going to get both transcripts that include both the exons and introns. And there's this get sequence function. It works pretty much the same way as this get BM function. The only real difference is you feed, instead of values, you use ID. You can also use a few other things to search by as well. So if we look at sort of the help thing here, you can use which chromosome and what the start and end position of the chromosome to also search by sequences. So you can basically retrieve any DNA sequence or peptide sequence or whatever. And then the next argument is type, which is what the ID we're specifying here is. So in this case, again, I'm just saying we're searching by gene name again. And then the sequence type that we're retrieving, in this case, I'm saying we want transcripts, including both the exons and introns for every gene, again, from the same MART that we specified earlier. And we'll just run it. It might take a while, this one. Yeah, this little stop sign comes up in our studio when you're running these queries, but it seems to be going really fast here. And now if we were to look at actually the sequences that we got back, you'll notice it'll truncate them. But basically, we've got a DNA sequence, or in this case, I guess it's actually the well, coding sequence for whatever the transcript is for every single one of those. So we only searched for, I guess, in this case, one gene. We searched for CIF. And then it came back, since there was multiple transcripts for the CIF gene, it returned one output entry for every single transcript. So we got basically 6 transcripts back, which is pretty cool, because usually you have to like search online and like on these bioinformatics databases, look for the name of the transcript and like download them all individually, but we got them all in one go. Does anyone have any questions on any of this so far? Or
is there like, so I've used this library a little bit, and looking at the writing all the time, like also these arguments, like you have a C type of argument. Is there like a list of all those things and what they actually are?
yes.
Like,
yeah, so that's kind of tough. And so it says it here in the documentation, but one of the things I noticed before the tutorial is that the documentation isn't all the way up to date, which is a giant trap. So you really have to play around with these queries a bit. So we're going to actually go to what we were doing before, which I know didn't work. So I fixed that before the tutorial. So I'm just, this get sequence thing. And you'll notice that in seq type here, it says allowed seq types are cDNA, peptide, 3' UTR, 5' UTR, and genomic sequences. Let's type in genomic. You'll notice in the comment that's what you originally said here. So let's just do that again, do genomic. And then it's going to go through a really funny error that says a completely different list of things to search by. Yeah, and so it'll give you this error. So look at this error. It says error in get sequence. Well, here's the function we just ran. It says please specify the type of sequence. And it says choose from these. And you'll notice that this doesn't match the documentation. Here it only has 5. Now there's 10 or so, and not all of these work. Let's try transcript exon. I'm pretty sure this one doesn't work either. Yeah, I know I'm trying to like advertise this package here, but this is definitely a problem to be aware of when using it. Not yet. I sort of discovered it while making the tutorial earlier. Doing this part of the tutorial earlier, last day or two. Yeah, and see it says not a valid attribute, although it should be. Anyhow, that's something for another time. You basically have to sort of try around a little bit to get the right thing here. Obviously, all the stuff in this tutorial works because I've tried it out and got it to work. But generally, if a query doesn't work, you've got to do a little bit of troubleshooting for what you're searching by. And there's one more thing, an example of how to do this later on. We'll get to that. But yeah, I should report that to the maintainers. Anyhow, when we retrieved all this information and sort of seek, so here's the different transcripts. It's actually sort of truncated them a little bit. We've got the transcripts basically plus the exon and intron and then the name. But how do we know which transcripts these are? Like, we don't have any information on that right now. Right now, these are all transcripts from this gene called CIF. But we don't know which, because these transcripts have an all individual ID. So what would be, I guess, a sort of a better way of retrieving it so that we got the transcript ID as well? Yeah? Okay, let's see if I can make the font bigger. Okay. Global options. Display. We'll go to 14 or 13. Can they see now? I feel like it's only going to make this stuff bigger and not actually the stuff down here. But basically the question was, so if I just do this seeks command again, you'll notice that we only retrieved, I guess, the gene name, as well as from this get sequence command, along with the actual sequence. But we don't actually know anything about the transcript IDs. We don't know what transcripts these came from or what the name of them is. So I guess there's a little bit of a smarter way to do this, and that's what we're going to cover now. we're actually going to try to search by transcript ID after grabbing all the possible transcript IDs from biomaRt. So why don't we just sort of do that, and you'll sort of see what we mean by that as we go through this. So I'm going to use this sort of get bm command again. With attributes, what we're looking for is, I guess, just the ensemble gene ID, again, the human readable name, and then we're going to get these transcript IDs. And again, how you sort of look up what these are is things that we could possibly use here is with the list attributes functions, the output of which I, again, have here. In this case, we wanted for this fly-based transcript ID. You sort of have to look through this for what you want. So what we're going to do now is basically, let's just retrieve basically a list of all the possible transcripts for every single gene in our gene list. And that was, again, extremely fast. It was working a lot more slowly when I did the search line. Anyhow, we got a list of basically, again, ensemble gene IDs, gene names, and also now you'll notice that we have different transcript IDs. So if we click on it here, you'll notice that there's multiple transcript IDs for every gene name, one per transcript that the gene has. Now, what we're going to do is actually do the get sequence command we did earlier. In this case, I'm doing peptide just to show that we can get a peptide sequence really easily to sort of get a different type of thing. And for ID, I'm going to feed it all of the transcript IDs from earlier. Again, we get the column that we want just using this little $sign thing on the transcript ID with the column we want. And basically, it'll take any vector of possible values. And then we're going to tell it that the sequence type that we're searching by is fly-based transcript ID. Notice that this is the exact same name that we used for up here when we were retrieving the attributes. And then we're telling it we want the peptide sequence and from the ensemble mark. And now you'll notice that basically if we look at, I guess, dimension of seeks, we have 70 of them, and we had the same number of transcripts, I believe. So basically, we got the same number of transcript sequences as we did transcripts. And then the last thing we want to do is, so right now we've got two separate queries that both have the information we want. So you'll notice that the sequences we got, so if you look at the sequences, so if you look at the sequences, you'll notice that we've got, so not the best view. We basically have the peptide sequences and we have the transcript IDs. And in the other data frame, in this transcripts one, we have the gene names and ensemble gene IDs. So I guess one of the things that you're going to do when you're using biomaRt is, so you see we've got all this information, you want to match it to some existing data and make sure it lines up with your existing data so you can sort of combine them into one glorious data set that has everything rather than looking at a whole bunch of different data frames. So to do that, there's this lovely feature called function called match, which is actually from base R. You don't need biomaRt to do this. But basically what it is, this is a little bit of a tricky function, but what it does is the first argument is going to be whatever you want to match to. So in this case, I'm trying to match it. So the transcripts is the one that has all the names of everything, the names of all the transcripts, the names of all the genes. And then the seeks is the one that has all the actual sequences. But between the two, they have a common column, which are the transcript IDs. So we're going to try to match one data frame to the other using these transcript IDs. And it's going to match them by row. So what I'm going to do here is we use match. The first thing is what we're matching it to, which is we're going to add all these transcripts sequences to the transcripts data frame. So we're using transcripts as our first argument. And then the sequences, since we're trying to match those, are going to be our second argument. So it's basically what we want to match to, and then the thing that we are matching. And then what does match return? If you look at the output of match, let's see what I call it. Okay, I called it index. It's just the list of numbers where the match in the second sequence was matched to the first one. So when we do this, what we can do is basically take the peptide sequences and return them in the order of the indexes in which they appear. I may not be making too much sense here. But basically, if we return the peptide sequences in this order, it'll match up perfectly to our existing data. And that's what the match function did for us. So the match function got the order in which the second argument, if you put it in that order, it would perfectly match it to the first. And if this match function doesn't find a match for something, it returns NA. So just something to be aware of. So what I'm going to do is basically make a new column in transcripts called peptide sequence. And it's basically just going to be the peptide sequence from the sequences we retrieved in the correct order. And now if we look at, I guess, transcripts, it's got all the names, all the gene names, the transcript IDs, as well as their actual sequences here. So yeah, we've successfully put 2 biomaRt queries together. And again, we can also do this. You don't have to just match up biomaRt queries with each other. You can also say you've got a data that was from a microarray or a sequencing data set, or even if you just wanted to find out information about a list of genes that you've got some other data with it, you basically can do the biomaRt query on, I guess, say, the list of the gene names, and then you can match it up to the existing data in the way that we just did. We're going to have one more example of this later today in which we do that. So if you don't get it now, we can cover it again. And now, I guess, sort of the last function I'm going to show you in the biomaRt package before we actually do the actual sort of like, I guess, sort of real life example is we're going to sort of try to export all the sequences for these files. And so I'm just going to make a folder, and the command to do this is this dir for directory create, and then we're going to make FASTA seeks. And you'll notice, oh, in my case, it already exists because I ran this tutorial earlier to make sure it worked. But it should make a folder called FASTA seeks. So if we sort of, if we start, say, a shell here, you should notice, and you just type in ls, or if you're in Windows, I think the command is dir, you should notice that this FASTA seeks folder popped up right there. So we just made that folder. What we're also going to do is fill that folder with, I guess, all the sequences that we just retrieved. And what I wanted to do is there's this wonderful little export FASTA function that comes with biomaRt. However, it's a little bit weird. So say if you've got all of the sequences back, such as here, it'll put them all in the same file. I want to put them into different files, one file for every gene. So you'll sort of see a little, I guess, way of sort of doing that. So what I actually ended up doing was making actually a function to do this. I'll sort of walk you through because I wanted to sort of apply this to all the genes in our data set and run sort of this function one time for every gene. Why don't we just sort of, I'm going to just set, I guess, sort of, the argument of the function is going to be the gene name. But here I'm just going to, we're just going to sort of run it through with one gene as sort of an example. I'm just going to do this fruitless gene, FRU. So what the first thing I'm going to do here is actually make the file name of what we're going to export. So this paste command, what you do is it matches strings together. So if you've got 2 strings, we'll combine them. And so what basically you specify a list of arguments, and it's going to mash them together. So in this case, I'm putting FASTA seeks / which tells it to put it in the directory. Then the actual gene name, and then I'm going to add .fa because we are making FASTA files, and that's the file extension for FASTA files. And then what's separating all these, it's going to put a space in otherwise. I've got this argument that says sep, and then just a pair of quotation marks with nothing inside to say there should be nothing separating things. But you'll notice that it makes a file name, and the file name, and this is what we're going to export the file as. the file name is going to be fastseeks/fru.fa. And the nice thing about R is when you save things with slashes in the file name, it interprets this as the folder to go inside, and then the next little bit is going to be the file name. So we've created the file that we're going to save. And then now what I'm going to do is I'm going to use a subset function, although you sort of are running out of a little space to see what's going on here, so we're just going to do that. And what I'm looking for is basically everything. So we've got sort of our list of all the different transcripts that has, with the gene names and all the transcript IDs. And then I'm going to say I'm looking for all the entries in that where the gene name is equal to, in this case, gene, which is FRU. And then the first argument of subset is the basically part of the data frame or piece of data that we are subsetting. In this case, it's just the list of transcript IDs. So when we do that, we basically have a list of all transcripts that match. Fruitless in this case has, it looks like 15, just sort of counting here. Yes, it's got 15 different transcripts. These are the IDs we want to retrieve. And you'll notice here that instead of just sort of exporting the FASTA files directly from that transcript files, we're actually going to export it from that seeks files, which is the raw output from biomaRt. Why are we doing it this way as opposed to just telling it to use the data frame that we just made of both of them? It's because this export FASTA function is just designed only to work straight off with the sequences that you get straight from biomaRt. And if you add any extra columns, it starts thinking all the different columns or stuff like chromosome name, chromosome position. It sort of automatically chooses what to put in the FASTA file based on what position things are in the data frame. And so if you don't feed it the raw output, it gets messed up a little bit. So basically what I'm doing here is I'm taking the seeks data frame and then subsetting it by basically, so we've got this sort of list of transcript IDs that we just made. And then we're looking for all of the transcript IDs in that seeks data frame that are, I guess, in this sort of %in operator. You may not have seen this before, but what happens is it basically just looks in whatever. So it's basically looking for if there's any sequences in here, in this vector, that are inside this one, it returns those ones. So let's just try to see if we can sort of take this command apart a little bit and run it separately. And it sort of returns a logical vector of which ones actually match that. So these ones that return true are all the sequences that are actually the correct ones that we're returning. And then this sort of sequences things here is what we're basically about to export, which is just one sequence for every single transcript that we're returning here. And then we're actually going to use the export FASTA function. And then I had the function return something which just tells you, hey, we're exporting this gene's transcripts. But basically, now if we look, I'm going to sort of go in here in the sort of shell. You can also go manually and say, take a look at the folders. Just if you look inside the actual folder, I'll just do that. Just actually, I think it's you should have a file here called fru.fa. And if we open it, actually it doesn't look as pretty when we do it this way. It should have basically the name of the sequence with a little caret here. This is how you sort of specify sequence names in FASTA files, and then followed by the sequence, and then one entry for every gene. If you look at it, I guess in a shell like this, if we're going to go into the FASTA seeks thing, we can sort of look at, and you can see it's got the complete peptide sequence for every single one of these transcripts. And you'll notice that it has multiple, I think we already showed this for another one, but it's got multiple sequences per file, which is totally okay in the FASTA format. You can have as many sequences if you want, as many FASTA sequences as you want in one file, as long as they have this little caret and then the name here. anyhow, that's basically the function I made to sort of export these and separate them by gene. Oops. But basically what I'm going to just do is if you hit enter on the entire function, it'll load it into R to be used later. And then I'm going to apply this function once to every unique gene in our little list of genes. And it should pop up and say exporting all the different genes. And now if you look at your folder, there should be a whole bunch more. But we basically exported all the DNA sequence, well, in this case, the peptide sequences for every transcript for all these different genes. Does anyone have any questions on any of this? Or it is sort of a lot of information taken at once, but it's pretty cool. If we wanted to just export, like I mentioned here, that the export FASTA function, if you do it on something, let's just try running export FASTA. And then I just fed it the seqs file, the seqs data frame, the whole thing that we returned from biomaRt, and then we just specify the file name. I'm just going to call it test.fa. You'll notice that it exported actually all of them. This is, we can sort of count them up here. We could do it's basically got, you'll notice basically there's 210 lines. That's one line for this, one line for every gene, every transcript name, one line for the actual peptide sequence, and then there's a space. So it's three lines per, I guess, sequence. And then there were 70 different transcripts that we returned. So it's got, well, 210 divided by 3 lines per sequence. It's got one entry for every single transcript. And so this little make FASTA function was so that I could actually split them up into files by gene. Any questions on any of that? Sweet. Do the online people have any? I was one of those in a tutorial a few weeks back, and that's how I wanted.
Oh, yeah. Someone was asking about if you could effectively use dplyr instead of match, difficult match logic. Yeah.
Evidently, left join, as he was saying, works pretty well. So, yeah. Yeah, I have to admit, we had the dplyr tutorial last week, and I was just like, I was like so indoctrinated into the old base R way of doing things. People do these new dplyr and plyr stuff, and it kind of confuses me a bit. So this is, I guess, the really old style of doing things. But you, again, can use dplyr and plyr to do this better in any other way you can think of. There's also a few things I wanted to add at the end. One thing is if you're doing stuff in biology, sometimes you'll notice if we look at that sort of list marts, this sort of, let's just do it here, head list marts. You'll notice that it returns all these different things, and they've got the versions here. This is generally when you do list marts, it always returns the newest version of everything. What if you don't want the newest version? This is sometimes actually a thing in biology, because say if you've got old annotation IDs, or like say like sometimes you're using gene names that can be a little bit older. One of the things that actually happens a lot, so if I go look at this thing, this ensemble gene ID, at least for fly genes, these change every time the gene annotation changes. Or occasionally they'll change. We didn't look at this information here, but the start and stops for every like where these genes are located on the chromosome can change between versions. So what if you need an old version of this information? I'm going to show you one way of doing it, and it's actually pretty simple. There's actually, when you look at sort of the list marts, you can say archive equals true, and now it pulls up older ones, all the ones that are actually in the archives and available for use. I'm actually just going to sort of browse through it a little bit more. I'm going to save it as old marts. And the reason I keep looking at things this way is because some of them don't really wrap. If we just tell it to print everything at once, it ends up looking really nasty. I found that while going through this tutorial the first time. But basically, you'll notice they've got ensemble release 47, 46, 45, 44, 43, which isn't all the ensemble releases. One of the things you might want to do is use other ones not listed here. For that, this is the simplest way of doing it, which you've got access to these. But if you want other ones not listed here, there is a way. But I would say look at the biomaRt manual, because it's a little bit more complicated depending on which release, which sort of MART you want to look at. And it's sort of, this is sort of the link to the biomaRt manual. And if you want to use one of these old MARTs, you basically just use that use MART function with archive equals true, and then it works just like normal, which is really handy. And so you'll notice that if we, well, if you list the data sets, actually, you probably weren't paying attention to the version numbers when I was doing this earlier, but the version numbers will have the version of each data set in there as well. There's also one additional sort of trap with this package that you sort of have to run into it before you're sort of aware that it's actually a thing. So you'll notice when we sort of did list attributes on sort of ensemble, and I'm just going to sort of take the number here. You'll notice there's 1,128 different attributes we can use here and different things we can retrieve. However, there's a little bit of a trap. You can't retrieve them all at once. There's this sort of concept called pages where there's sort of different types of things that are sort of listed on their own little internal page, and you can't retrieve things from separate pages at the same time. So how do you know what's on a page and what's not on a page? This probably won't happen to you, but if it does, this is how you get around it. There's this sort of attribute pages command, which is all the potential pages that there are to retrieve stuff from. And so there's the feature page, structure page, homologs, SNPs, somatic SNPs, sequences. So how do we look at what's on a page? So these are all the possible pages. If you want to look at what's on a page, you can use this list attributes function, and there's an optional page argument. In this case, I'm just going to say SNP. And it returns these are the attributes we can look through.
Oh yeah, I just want to add, this is like one of the points that screwed me up when I first read this.
It screwed me up so many times, and I'm like, yeah.
So another way also is to, if you want to look at everything and different pages,
Ooh.
the argument of this attribute space called what. It's like you say what equals an vector load page description, gives you everything in the list with the description.
Let's try that right now. So you're saying it's the
So if you do, yeah, you list
what?
attributes.
Okay, and I'm going to say what equals, actually I'm going to make a new line here. That is really helpful because it saves browsing by pages. So what equals,
Yeah, the vector with name, page, or whatever.
doing it in the wrong order, eh? All right, let's try that. Oh, I'm missing a parentheses. Okay, let's just do that head again.
Yeah, that's just, or you can just like,
Oh, there we go.
yeah.
Um,
If you look at that
Yeah, let's just save that as ATR. Let's look at that in the little RStudio browser. Oh, that's wonderful. So now, okay, you should do it that way. So when you do list attributes, say what name page description, because then you will save yourself from this awful, awful trap, and you'll know how to not get this wonderful error when you retrieve things from multiple pages. If you do want to retrieve things from multiple pages, you have to make separate queries, and then make sure the separate queries have, I guess, the same thing. Let's just see if we can scroll to the end of feature page. You'll notice that there's a different page for structure, and there's a different one for, I guess, feature page. If you make separate queries for all the separate pages, and then at least have one common elements, such as ensemble gene ID, you can match your queries together, even though you had to make them separately. And so you can combine it all together afterwards. Anyhow, that's the end of, I guess, that part of the tutorial. And then I had one sort of real world example, which was actually sort of showing how to convert gene IDs from one version to the other. So what if like you had really awful non-human readable ones and you needed to convert it to something intelligible? So that's what I was sort of going to cover, because I think that's like the biggest, it's probably the stuff I use biomaRt for the most, because it's totally a lifesaver that way. So we're going to open up this GTF converter.r file. If no one has any more questions or anything. Awesome. Cool. So this GTF converter, and I'm actually going to clear all these things, these environment variables, just because I like to have a fresh start. But basically, what we're going to sort of do here is there's this really complicated file format called GTF, and it's used in a lot of sequencing applications and also just general bioinformatics. We're using it here because it's complicated, and it shows how to like use this on like a real file that might be potentially tricky, and I guess overwrite it with the same file and not mess up the format. Basically, if we look at one of these things, I'm just going to sort of blow it up here. So I've got it called, we're going to do this dmail gene set abridged. And what this is just, I think, the first 10 or 20,000 entries in this GTF file. But the bigger GTF file, I've got one sitting around somewhere, has everything, and it's like 300,000 elements, and which I figured would take a long time to look through with biomaRt. So we're going to do a shorter one. But basically what the files look like is, I'm just going to sort of load it here. Is it sort of like this tab delimited file. The first column is the name of the chromosome or contig where a feature came from. The second column is where this information came from. In this case, it came from Flybase. The next column is what kind of feature this is. Is it an exon, pseudogene, or I think the other one in this file is also a coding sequence. This next column is the start position of this on whichever contig or chromosome it was. This is the ending position of it. This is actually, it's not really part of this file because this is the official Drosophila gene set. So there's no information here on this. This is the confidence of the feature actually existing. Some programs will give you a confidence value for how likely a feature exists if it's generating these GTF files. This plus dot or minus just tells you what strand of the DNA it's on. So this one with the dot means it's not a feature on either strand because it's just a pseudogene. It's not actually a real, I guess, gene. But this one tells you it's on the plus strand. This one's on the minus strand. And then this one, it's either dot minus or, I guess, a 1 or a 0. This is the frame of what a particular feature is on. So like there's 3 possible frames. There's 0, 1, or 2, I believe. Yeah, 0, 1, and 2. And this is sort of how offset it is relative to other. Basically, you know how I guess genes are sort of translated 3 codon, like 3 letters at a time in codons. This sort of tells you the offset of that. That's what the frame is. Anyhow, the 9th column, the important one here, has the transcript ID, which is the name of each transcript that we're looking here, as well as the gene ID where this comes from. In this case, I was actually giving this file to some other people to use for a sequencing application, but the problem is when it comes out, the output is all in these unintelligible FBGN numbers, and they wanted actual gene names because that's easier to look at. So what we want to do is convert all these unintelligible FBGN numbers into actual gene names. And we're going to use biomaRt to search for what gene name corresponds to all these numbers. Anyhow, and that's basically the goal here. And that's what this file will do with a lot of comments and like displaying the output in the meantime. So this is a kind of complicated file. And so to load it into R, we've got to be sort of clever about how we do it. So there's this read.dlim function, which you can use to read tab delimited data. The first argument, again, just what we're loading. Header just tells it that the first line is, header equals false tells it the first line is not actually a name of all the different columns, because that's not part of the GTF format, so it doesn't automatically just chop off the first row and we lose that data. This as is, R really likes to make different, when it sees characters, it likes to make them into factors, which is not useful for us at all. As is tells it to not start turning everything into factors. And then this quote thing here, you'll notice that when we looked at this data, there are actual quotation marks in this file. And if we don't use this quote and then tell it nothing is the quote character, it'll erase all those quotation marks. And I wanted to use the quotation marks later. So anyhow, if we enter this lines, it should load, again, 20,000 entries. That's basically loading the file. And if we look at it, we've got 9 columns, which is the same as what the file has. So again, all those same things I just described. And then the last column is this ugly thing, which was the stuff where we actually want the data from. And these slashes are just escape characters preventing R from ending the string at that point. So that's the way you add I guess in this case, a quotation mark into actual string in R. So what we're really only interested in here is all the information that we're going to use to search biomaRt by is what we want are these gene IDs, because we want to search biomaRt by these gene IDs for the actual gene name. So we somehow need to get those. Anyhow, there's this wonderful, well, first we're going to take the 9th column because that's the one that has our interesting information. And if we look at it, you can see one line for every single entry here. And then what we want to do, Hedley Wickham's string R library has this nice function called string split. Is I'm just going to, I'm sort of abusing the fact that there's these quotation marks in these really lovely spots. There's a quotation mark directly right before the transcript ID as well as the gene ID. And because of that, we can use that to basically, the string split will split each of these strings at those quotation marks. So when we do it, oops, I didn't load the library. Now when we look at the head, I guess, of metadata, now you'll notice it's split into column. Basically, actually, it's a list with 5 elements per list. There's the transcript ID name, and then there's the actual ID. And there's the gene ID with another, basically all the other formatting we didn't want. And then there's the actual thing that we wanted to search by. And of course, it's in a list now, which is not particularly pretty. So what I'm doing here, this function is just a cheap way of turning something from a list back into a data frame again. And when we do it, now if we look at metadata, you'll notice it's now basically, in this case, it's actually a matrix, which is just a data frame, but without us, we can't have different things in it. That's the only difference between a matrix and a data frame is that a matrix, everything has to be the same type of thing. In this case, it's character elements, whereas a data frame can have numbers, characters, factors, everything. Anyhow, so basically now that we've got this matrix, we know here that the 4th column has all of our actual gene names that we wanted to search by. So if we did like head metadata, and then we took the 4th column, whoops, it comes out with all of our gene names. So now, what I'm going to do is load the biomaRt library, although it should already be loaded. But and then what I'm going to just do is get all the unique values, because these queries go a little bit faster. Although they're growing really fast today, it's not usually this easy. And what I'm just going to get is all the unique gene names here. So we only search for every individual entry once. And so once we've done that, we should have a list of, I guess, let's just do a length of the length of. We have 1,127 unique genes that gene IDs. And so what we're going to just do here is, again, we're going to use that same ensemble mart that we went and used earlier, and the same data set. I'm skipping all of the list marts, list data sets, and then stuff because I already know what I want and know which database I want to use. So again, that connects to Ensemble and it stores how to connect to it. And now I'm just going to basically search for two attributes. All I want are the Ensemble gene IDs, which is what these gene IDs are here. And then I'm going to search for the actual English gene name, which is for this fly-based name gene that we were using earlier. And then we're searching, in this case, we're searching by the Ensemble gene IDs, because that's what we've got here. And then we're going to use these values that we just calculated, which is a list of all the unique genes, and again, using the MART from before. So let's run that. Now, we should have a little data frame with our Ensemble gene IDs and all the actual names, which is pretty sweet. We've got all the names. So what we're going to do now, we had another example of this earlier, but we're going to do it again. We're going to use that match function. And again, this is what we are matching to, and these are the things that we are matching. So this is the data we just retrieved, and this is our data that we want to match to. Now we have an index for all of the different things, for the order that we want to return things. And you'll notice that there's an NA in there. NA means it didn't get a match for what we looked for, which sometimes when you use biomaRt, like really en masse here, you'll get NAs like this where you weren't able to retrieve something because that value for something wasn't actually in the biomaRt database. So so basically we could try replacing, I guess, everything at once, or we could just try to replace all the things that are not NAs where we actually got values for. So that's what we're going to do. So what I'm going to do here is basically get first I'm just sort of splitting, I'm returning so the biomaRt data that we just retrieved, and then the gene name, and then I'm going to return it in the order that we just calculated. And you'll notice that I'm calling that replacement. Again, it has an NA, so if we were to just try to replace that column in our data right now, if we try to replace our old gene names with what we just got, we would end up writing NAs into gene names, which would be bad. What we want to do is, although we could probably spend more time trying to figure out how to retrieve these NA genes, like use older annotations or potentially other ways as well, I'm just going to basically replace everything that's not an NA. So what I'm going to use this sort of function called, well, is NA, which will calculate whether or not everything's an NA. And then the exclamation point means not all of those. So instead of, basically, is NA will return a whole bunch of true and falses. The not will switch the true and falses, because it basically means not true is false, not false is true. So when we do that, we'll get a whole basically an index of basically true or false. And then this which command just tells you the indexes of which ones are true. So basically, it just told us which indexes in replacement are not NAs. And then basically, I'm going to replace all of those indexes where we didn't have NAs in both data sets with our new data. So now, if we look at our data, you'll notice that basically it has actual, I guess to say English or human intelligible gene names that we just retrieved. In the case where we couldn't retrieve something, it still has the old ID. And in this case, you can see one of the reasons it failed here is it had a transcript identifier here, because it says if it was a gene ID, it would see FBGN and then have a number, but in this case, it's FBTR, which means fly-based transcript, which means we wouldn't have been able to find it with that query. So, which is why it was NA. Anyhow, so basically what we've done now, so if we look at our, I guess, metadata column, you'll notice that, yeah, it's got all the replaced gene names. So we want to put that back into our original GTF file and have it still be intact so that when we use this GTF file with other programs and stuff, it'll still work. So what I want to do, well, I guess the first thing we've got to do is smash all of this back into one column, and so that it's all, we want to basically have one column of values, which would basically combine every element in each of these rows into one thing. So what I'm going to do here is I'm basically just making one. This is just making a whole bunch of a column of quotation marks. It's just as long as that's our data. And then we're going to use this paste function again. We used it before. It just mashes strings together. And then I'm just going to tell it, basically put the first column of this metadata thing, which would be just the word transcript ID over and over again. Then a set of quotes, lots of quotation marks. And then I'm going to put the second bit of information in. We're basically just putting those quotation marks back in because that string split command we did earlier got rid of all the quotation marks, and it needs those quotation marks to be valid. So now when we look at it, it's just one long line, which looks exactly as it did when we started off. And now I'm just going to add it. So basically, we've still got this GTF thing, which is where we got all of our data from in the first place. And I'm just going to replace our ninth column with the new ninth column. And now if we look at it again, it has the actual gene names. Looks like, yay. And then if we want to export it or write a tab delimited file, I'm just going to basically, you can use this write table function. Again, I'm just to say, I'm just telling it we're writing the GTF data frame. This is the file name. And then we want to have it be tab separated values. If you don't specify the sep argument here, it makes it space separated, which is really frustrating. And then we don't want to add row names because R likes to do that. And we don't want to add column names because, again, that's the thing that R likes to do. And then we don't want to add quotes every time we use a string. So when we do this, it'll write out this file. And then when we look at the file again, the new file, let's do that again. So it's actually, okay, well, this is as good as normal. You'll notice that now the gene IDs, because it's sort of wrapping around here, the gene IDs have now been replaced with the new things, in this case, CR41590, but it actually has things you can understand. So this one has L2, GL, I guess that's the name of the gene there. But we've successfully replaced all the gene IDs in this file, and it has the identifiers we wanted to use in the first place. So that's, I guess, an example of how you can use biomaRt to convert bad gene names to something that you would rather work with. So, I mean, I know that was a lot of stuff to go through in an hour, and you guys have been kind of quiet. Are there any questions about anything? It's sort of the goal that, like, maybe you might not use it now, but now if you want to retrieve some of the stuff from, say, online databases, like you need information on gene, you can hopefully refer back to these tutorials and be like, oh, that's how I get it, and go through everything again. So, cool. Any questions from the webcast people?
So for everyone here, they were planning on the biomaRt and browser soon, and want to publish the cool. They want to do it. No, it's just, no, but like I did biomaRt, like the website, yeah, on the portal. And you export it in with the EPUB, and then open it in Python or something like that. It was just the next time I did that.
Yeah, there's also like the biomaRt has an API for the website.
Yes, you know what?
Yeah, that's what this uses under the
Mm-hmm.
So there's a Python package for doing this, and there's also a Python package that runs the R package underneath of it. That does this as well. So if you want to say Python,
A Python package that runs the R package. That's it.
yeah, well, all right, fine. Why rewrite the?
Yeah.
Just another example of something that for is there's the old Polylogs page.
Mm-hmm.
Page. So like we really start to want to the treatment rates and changes and stuff like that.
Mm-hmm.
Use biomaRt, pull down all the every single CVS from a single bag, and they have like pre-annotated envelopes for every single or every single other species in some database. So you build a phylogenetic tree of genes for every single gene in the paper, the processing until it's all but very super handy.
Yeah, it's sort of like if you need information on a gene or like protein or anything, you can just get it all with this. And so eventually, I mean, you probably won't use this all the time, but when you do use it, you're like, oh, I just saved what would have been 8 hours of work, just like, going to every gene website individually, taking some notes.
You've also got a record of exactly what the data set was in that first. Always use it on your script.
Yeah.
Is there any rate limit on this? Like, can I just set up a little block and start sucking down absolutely everything that biomaRt points at?
I haven't ever had a problem using it. The only time it's ever got been a problem is like when the internet disconnects like halfway through or something. But I don't know. Go crazy.
It's like the font version. Use font between everyone. You want the full thing to actually work.
And some people make copies of also, maybe one reason why I was slow this morning is you're just not going to bed.
Yeah,
when you're off of lunch.
I think it might actually just be the internet isn't that great over in LSI sometimes, but and maybe it's just better here. But yeah, that could also be it. I sort of imagine whenever I'm doing these, it's like, oh god, he's just continually asking for the like. I sort of imagine almost it'd be like someone judging me on the other end. It's like, what is this? A typo? Oh, rejected. But yeah, and that's like actually this package doesn't actually have that many functions. You're just usually sort of using the same functions over and over. We have actually covered almost every single one here, so. Which is, I guess, sort of rare for these kind of tutorials.
And then I would search for 1,000, like that was very difficult to expand into.
Yeah. So I guess what's your sort of end goal? Do you want them all just in like one line of Go terms, like one list, or?
That would be nice. Like the most specific, like your child.
Yeah, because I feel like I know you can attain the Go level, so you can get the child terms or something. But you're still going to get multiple different types of Go terms from that. But one thing you could do, which would involve a little bit of, I guess. Yeah.
So Go is the gene ontology.
Yeah, gene ontology. One thing you could sort of do is basically just when you retrieve that massive data frame that's been expanded into oblivion, I guess you could probably try to you get basically all the unique Go terms for each gene, and then you can sort of play around. You basically just take the Go terms for every gene, and then you just sort of use basically I guess just sort of clever string handling to try to put them into one line. Again, I can't say exactly how to do that off the top of my head, but the reshape package is pretty good, and or the reshape2 package or whatnot. But basically, all the sort of standard like data handling things in R, you could probably use that. And then as long as you had something to match that back up to the original data set, you could put that new line of reformatted Go terms back in there. But yeah, it's really frustrating if you've got a list of Go terms and then just made your data frame explode, I guess. I have totally had that happen to me before.
Any questions for Jeff?
There would ever find like that you would find a place where they actually have like more than a description of all the attributes. That would be incredibly valuable thing. Things like it'll be like gene start, and then it'll be like genomic start. And
Yeah.
And then the description is the repeat of those.
That would change depending on data if you're doing
Yeah, the attributes definitely do change between which database you're doing, and like one of the things you can get here. So it's like, how did you know that what you want are ensemble gene IDs and this fly-based named gene, how do you know that's what you want? Because when we did it, say I do it like, let's just do it, I'm gonna just do it, store this attributes thing. We're gonna just list all the attributes. Ensemble. So when we do that, we've got all these things, and it's like incredibly vague because sometimes like, what's the annotation ID? Like, what is that? And you've got to sort of, I guess, when you're figuring what you want, you sort of just have to retrieve it first and see what it is.
Yeah.
And like he was saying, there is not actually any, you've got to sort of get whatever you want first before you can figure out what it actually is. Yeah.
Is there anything like this for NCBI? No,
Yeah.
they're not part of it.
Yeah.
Yeah, it's just good. It's just like the wild west, which that they're not. That's what we use all the time.
I think you can probably, they might have some NCBI information here. Ooh, the SRA is pretty good. Yeah, so can you just pull down like all the descriptions of what things are, and then, oh, that's awesome.
Yeah, that's where it is like this weird like projects.
Yeah, it's a maze. It's a maze. Like you can.
If you know that, then you
That's awesome. I'm gonna have to check that one out. But basically, I mean, it's got all of these different accession numbers for all these different databases. And so one thing that's kind of useful is you can potentially get. I mean, there might be NCBI stuff in here somewhere. You've got to, I guess, look, but potentially the information you're looking for. At least it's a good way to figure out if you need an ID from one database, you can get the identifier for it with biomaRt. Any additional questions before I terminate the web stream and close down for today? Sweet. Okay, let's turn this off. Yeah, no problem. Yeah, we're going back to, I suppose you missed the inception, but it sort of takes a picture and shows you what the web stream is, and so you get this endless thing. And if I notice if you move the mouse, it sort of repeats on infinitely. You can see the mouse moving in all those alternate realities.